This is the second example showing how to take a function and decompose it into even and odd portions. As a reminder, the reason we care about breaking any function down into even and odd pieces is because it's going to make it easier for us to analyze that signal, as we're going to see in a few weeks. So let's, as our signal to analyze, let's do something a little different. Let's have a non-periodic signal, unlike the sinusoid we did last time. And I'll have a triangle that starts at 1 second, ends at 2 seconds, and does a linear ramp up to 2 volts, and then suddenly drops back down to 0 volts. And outside of that 1 to 2 range, this function is just going to have the value 0. Now I can see that's not even and it's not odd. If I flip it about the horizontal axis, about the time axis, all of a sudden I have a peak from -1 to -2 seconds. And I don't have anything that looks like either a inverted or non-inverted version of what I started with. So let's see what happens with the even and odd decomposition approach. So we know from the lecture and from the textbook that to get the even portion, to force the signal to be even, you take the signal and add it to the time reversed version of the signal, and then you divide by 2 to get an average. So if I take a look at what's going on here, what I have is I have graphically 1, 2 seconds. I have the original signal, and then I add it to the time reversed version, and then I divide that result by 2. So instead of being 1, this has a height, instead of being 2, this now has a height of 1/2. So that's my xe of t. And I can see indeed it is even. If I flip it about the time axis, I get the what signal I started with. Now for the odd, I have a couple approaches and they'll both work pretty well. I could either say, well, let me take x of t and subtract x even of t. That's what we did last time, and that's a perfectly fine way to do it. Or I could say, let's do this other average where I had x of t minus x of negative t, and let's build the signal that way. So if I do that, let's draw this from this second definition here. It says you take x of t, okay, so x of t is on from 1 to 2 and spikes up like that. And then I subtract, so I have the negative values of the time mirrored version. So the time mirrored version, that's what we called it when we replaced t with negative t, is the same time mirrored version as we had up here for the even component. There's the time mirrored version. But I also invert it in the case of the odd function. So I take these positive values and I'm going to make them negative values here. So from time -1 to time -2, I have that. And I divide the original height of 2. The formula says divide in half. So again, this is a maximum of 1, and that goes down to a minimum of -1. Now, if I add these two signals together, the even portion and the odd portion, if I add these two together, we can see this and this cancel out because they are the negative values. And this triangle and this triangle, they're the same value. They come from the x of t over 2 here, which is the same in both formulas. They're going to add up, and I'm going to get up to the original height of 2 instead of 1. So when I have a function that only appears in the first quadrant, this is the pattern we see. We see the even and the odd have the same first quadrant portion, but in order to make it even, the second quadrant portion is a mirror image of the first quadrant portion. And then for odd, I have to have negative of those values. So my second quadrant part comes down into the third quadrant, and I have that making up the odd portion of the signal. We will see this pattern repeat for any signal that is purely in the first quadrant.